You can take the mic.
Well, usually I don't need it. Yeah. Usually I don't need this. You guys are pretty rowdy. It's my honor and my pleasure to introduce Victoria Stodden. She's an assistant professor of statistics at Columbia, and she received both a PhD in statistics and a law degree from Stanford, and also served as a postdoctoral fellow at the law schools at Harvard and Yale, and at the Sloan School at MIT. Currently, she's serving on the NSF Advisory Committee for Cyber Infrastructure, so it's very fitting that she's here to talk about this exciting topic. So welcome, Victoria, and we look forward to talk.
Thank you. Thank you. So I've heard trickles of what I'm going to talk about in some of the other talks and presentations and discussions today, but I thought it's very nice to actually go at the end, too, where I can tie all these threads together that I've been hearing. So I wanted to also just mention that some of what I'm talking about was inherent in how I was sort of brought up as a PhD student. My advisor was David Donahoe, and we were always taught to, when we released our work, we released the code and the data that went along with the work such that it could be reproduced by other researchers. And so this was something kind of in the air that we were breathing then. And so a lot of my work since then has kind of been a revisiting of this and an amplification of these ideas. So to start with a few motivating examples, this isn't news to anyone in this room, but of course, computational sciences in general, research in general is subject to this enormous data deluge. I pulled a few facts out. You guys could probably even give me a few more, probably even more impressive than these. But so one of the projects, the Large Hadron Collider, the CMS project, they tell me that they're pulling off, when the collider's actually working, 780 terabytes a year, and then of course they process this, and then it goes into the petabytes, and they're struggling with how to work with and how to store this data such that they can replicate their experiments and store it even as open data. So it's an enormous problem. Sloan Digital Sky Survey, any of us can go get sky images. The current release, I think, is 50 terabytes. And of course, that's not something we're just going to download onto our laptops and fool around with. And even in the social sciences, so outside what we would consider the traditional hard sciences, there was a report by Laser and other co-authors in Science magazine a couple of years ago saying how social network data and this avalanche of data is revolutionizing political science and sociology and other disciplines in social sciences towards a real quantitative revolution like they've never seen before. And they're confronting these issues as well that we've been talking about for 2 days. There was a survey that Science did of their users in February, and they got, well, not their users, their peer reviewers, and they got 1,700 responses, and of those, there were 340 of them regularly working with data sets that exceeded 100 gigs. So maybe in our discussion, that's suddenly considered small, but that's still an enormous amount of data to work with, in my opinion. And 119 regularly working with upwards of a terabyte. So this is something that is bringing new methods of communication about how we actually tell other scientists about our work and how we do peer review and how we do verification and validation of the results. So that's one big change. Now, this is coupled with two other very deep changes that people talk less about, but I believe they're equally as important. We're doing massive simulations. For example, complete evolution of a physical system. We tweak a parameter. We can run the simulation again. There's a beautiful poster out there I saw doing exactly this. So this is a new way of doing scientific investigation driven by, in part, data and also, of course, computing power. And then the one that almost nobody mentions, which I think is just as important as everything else that's driving these changes in computational science, is now the code is really housing very deep intellectual contributions that are being made to science. And that might not be remarkable, except for the fact that these contributions are in the code exclusively. They're not making it into the paper. And so now code, I think, is being elevated to a medium of storage of intellectual contributions to science. So all of these have, I think, very deep impacts. So what I did to understand how this was changing scientific communication, I just looked at the Journal of the American Statistical Association. As a statistician, it's one of our flagship journals. And I was interested in how data and code release had changed over time. So I looked at 1996. what papers had a computational component, and if they did they tell me where I could get the code and how I could actually rerun or verify the results that were in that particular paper. So you can see in 2006, slightly less than half of these articles had a computational component. Of course, the other ones were doing mathematics. None of them talked about where I could get the code. So there were figures and there were results and tables in there, and there was no way for me to reach in and see what the code was that had generated these results. Fast forward 10 years, 2006, nearly all are computational. We have 33 out of 35 now are computational articles with some element of computation in them. 9% are talking about where to get the source code. So, and I was very generous with if you made it into the code publicly available category, if you talked about where I could get your package or pointed a link. It was a very low bar to get into that bin. 2009, and also this year, this June that just went by, every single article that's being published in JASO now has a computational component. So it looks like this is here to stay. We're up to 21% that are talking about where I can get the code to actually check the results. Now, this wouldn't be so much of a big deal if we could be confident that all the information required to reproduce these results was contained in the paper. And I don't know if any of you have actually taken a paper in your field or whatnot and then actually tried to regenerate the results based on the description in the paper. The way that we communicate computational work is from a pre-computational era. So we would talk about a methods section or have a pseudocode description of what we're doing. And this is a far cry from seeing what actually happened in the code, not only because you don't get to see that the code is actually doing what the paper says it's doing, but a number of small details that are implemented in the code, they just don't have a way of getting into the paper, like what exactly were your parameter settings, what exactly were your function invocation sequences, and how exactly did you produce those results. And we all know as computational sciences that even small changes in any of those could dramatically affect the results that you're getting. So they're very important. So what's happening now is, and this is not something I invented, but this is something that is being regularly talked about in a variety of different fields, that we're actually engendering a credibility crisis in computational science now. We don't have, generally speaking, shared data to validate, verify, reproduce these results, and we don't share the code. We share a loose description of what happened. So this is my advisor, David Donahoe, and we've been thinking about these issues, and he has an argument that computational science is not yet elevated to a branch of the scientific method. And the thinking goes like this. So thinking about what comprises science, we can go right back to the Greeks and we talk about systems of deductive logic. And there it's very clear, and we of course still have examples today in mathematics and logic and so on. It's very clear what comprises a contribution to science. You would not publish a mathematical result without a proof, and people know what this proof is. It's hard to kind of, slip that by mathematicians. So, but those standards are there, and the standards for what a proof is, and a standard for how others might replicate that work. I mean, I'm not saying it might be easy necessarily, but there are standards in place. In the empirical branch of the scientific method, similar standards were developed for reproducibility. What this meant is there were structures of hypothesis testing, controlled experiments. There were also structures around how you would communicate the results. For example, there is a methods section, and you wouldn't publish, say, a bio paper about a discovery in your lab and skip the methods section, for example. Very similarly, you just wouldn't skip the proof. So there's a lot of discussion about computational science being a third branch of the scientific method. There's discussion about the data deluge and data-driven research being a fourth branch of the scientific method. So the argument that I agree with and I'm presenting to you today is that we're not quite there, and that isn't quite right. And the reason is because this field is very young, and we haven't yet developed those same standards, like the proof, like the methods section, and the communication standards that allows us to call computational science as practiced today a branch of the scientific method. So the main motivation in the scientific method is rooting out error. Then the notion that the ubiquity of error in everything we do, and how we need to always have on the forefront of our mind an awareness of this fact and standards built around how we have addressed these errors. So what I'm arguing is that in computational science now, only a few decades old, you can see in talks and conferences when people present new results that somehow this notion of the ubiquity of error, this notion of a scientific communication being about rooting out error has been lost. And oftentimes what I've seen and what others have seen is instead you see what we call in one of the papers breezy demos of results or implementations of algorithms without a real effort to convince people who are watching the presentation or reading the paper that you've done everything you can to root out the error. And this is something that's being talked about. There's a Ioannidis article, Why most published research findings are false, talking about medical science. And you've probably been aware in the news over the last few years, issues like ClimateGate or this scandal at Duke over clinical trials. Those can be interpreted as failures of reproducibility and failures of communication of the code and the data. And this doesn't just undermine our science as it's practiced, but it undermines the public perception of science as well. So what I'm arguing, the main thesis of my talk, is that our framing principle for communication of our scientific results needs to be reproducibility, and we need to go back and visit that very old, from the 1660s, concept that we've had in the scientific method. Donahoe has a quote that I think encapsulates this idea very well, and I'll read it to you. The idea is an article about computational science in a scientific publication is not the scholarship itself, it's merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions that generated the figures. So you can distill that down to a simpler definition. A result is reproducible if a member of the field can independently verify the result. This is a definition used by Gary King in political science, for example. So if we think about reproducibility and think about it as a framing concept, there are very nice corollary effects. So it's not just about scientific integrity. Reproducibility also gives us a tool through which we can understand how to scope the sharing of data and code. So there's lots of discussion in policy circles, and I've heard discussion here about open data and so on. And this is a daunting concept. Like, what does open data mean? Is this going to change how I actually practice as a computational scientist? Do I just need to buy a bunch of disks and put things online? And what do I share? Do I share every version and every change that I've made? And what about updates? So if you think about a published result and you think about reproducing that result, it becomes much more clear about what's important to share. And you can share the data which then generated the results, and you can share the procedures that you've done to that data. Now, that's not saying it's easy, but it's saying that the problem is then scoped in some kind of coherent way. So speaking of it not being easy, so the rest of my talk, I'll go over some of the challenges to implementation of this ideal of reproducible research that I believe that we are going to have to face and are beginning to face. And I've been studying this issue for 2 or 3 years now, and great strides are being made, and a lot of interest is coming up from many different fields in computational science, and I believe we're accelerating this process. So this is something, as computational scientists, we're all going to have to confront, I think, at one stage or another. So as computational scientists, we're subject to incentives from a variety of different sources. So what funding agencies who give us our grants demand and what's in their grant guidelines certainly influence the decisions we make as computational scientists. Every school, I think, that has a tech transfer office has researchers who are subject to incentives to patent their research and to commercialize their research. And this is a different set of incentives than sharing your research upon publication, for example. There are intellectual property constraints, and I'll talk about this a little bit more a little bit later in the talk. There are very strong incentives that come from institutional expectations. Largely, particularly young researchers will do what it takes to be approved by a tenure committee or a hiring committee. And if these committees are not aware of code sharing and data sharing, which is not an easy task, it doesn't make any sense for that researcher to engage in those tasks when they could be getting more publications or things that will be recognized by the committees that they're trying to impress. And then another set of incentives that's visited upon computational scientists is acceptance in journals. So what do the journals demand when you submit a paper and have a paper accepted? So all of these sources, in some sense, you can argue that they need to be working together and in concert to pull together something like reproducibility in computational science. Okay, so the first thing I'll talk about is what's happening at funding agencies and the influence of funding agency policy. So this is another blizzard of words that I don't expect you to read, but I'll summarize for you. So it may surprise you to know that in the grant guidelines for NSF, there's very strong language about sharing code and sharing data. And in fact, the NSF expects investigators to share with other researchers data, samples, physical collections, other supporting materials created through the course of doing work on this grant. So there's this expectation that's already built into NSF, and I think I looked at the 2005 grant guidelines, and probably it goes back further than this. So this is something we're already subject to. It even says it encourages grantees to share software and inventions and otherwise act to make the innovations they embody widely useful and usable. Okay, so we all know that this is not enforced. But it's sitting there, and it's sitting there in the grant guidelines. And just this January, probably people are aware of this in this room, but the NSF started requiring 2 pages to be submitted with every grant application describing your data management plan. Now, these were largely open-ended. There's not a lot of direction from NSF about what should be in that plan, but it feels like NSF is really thinking about data. NIH has similar plans, and it says, or similar ideas in its grant guidelines. The NIH endorses the sharing of final research data. So slightly kinder language, right? It endorses the sharing. It doesn't require the sharing. To serve important scientific goals, NIH expects and supports the timely release and sharing of final research data for their very big projects, more than $500,000. Okay, so it's there. So a little bit more about the data management plan. This is essentially the announcement. The supplementary document should describe how the proposal will conform to NSF policy on the dissemination and sharing of research results. So I don't have any inside information from NSF, and I wasn't involved in the data management plan, but it sounds to me from the wording that they're looking to how do we enforce these grant guidelines. If you think about your own projects and how you would share data, and you think about your neighbor's projects or people in another field, what's required may be quite different, and there isn't a sense that a one-size-fits-all or a requirement you must release data is going to have any effect or produce the desired ends of reproducibility. So my read of this is that the data management plan is one step to understanding how the community will respond and how the community can share data. Add that to the fact that the data management plans are peer-reviewed as well, which means that there's a large amount of community influence and judgment that's going on with the data management plans. Okay, so the language of description on the NSF website about the data management plans mirrors that in the grant guidelines. So it looks very much like they're trying to do an enforcement and implementation of their grant guidelines. Okay, there's also discussion happening in Congress, and I'll give a smattering of this discussion as well. This is something that I don't believe computational scientists are particularly engaged in. And there are a number of regulations and laws that happen that very much affect how data is shared. Open data is something that's being discussed widely, and I think it's a shame that we're not more involved in that discussion and debate, simply because since the laws affect us, this formation of policy and regulation can be captured by groups that have special interests or regulatory agencies who may be very concerned about how data is shared, and we may end up with policies that don't actually suit our scientific ends. And we already have that in place, and I'll give an example in a few minutes of copyright that certainly is something that's a congressional act that doesn't help us do good science. Okay, so earlier this year, Congress reauthorized the America Competes Act, and I wanted to point out a couple of encouraging things about this. So encouraging in one sense and calling for engagement in another sense. So sections 103 and 104 have some interesting words in there. 103, Interagency Public Access Committee needs to be formed to coordinate federal science agency policy, research and policies related to dissemination and long-term stewardship of the results of unclassified research, including digital data. So that's my italics in there. But the fact that they're talking about data means they're talking about what we do. And I'm going to guess most people were not aware of this that's coming down. So there's a committee, so this isn't regulation on us yet, but there's a committee that's looking into this and how, for example, the White House can act in this and how Congress can act in this. So Section 104 speaks directly to the White House. The Office of Science and Technology Policy shall develop policies for the management and use of federal scientific collections to improve the quality, organization, access, including online access, and long-term preservation of such collections. So they're also talking about sharing data and sharing scientific data. So these things are in people's minds. So I want to talk also about an older act that has an enormous amount of impact on what we do here in institutions in research, which is the Bayh-Dole Act of 1980. The first thing you note is the 1980. So this was passed on the eve of the digital revolution, and I could almost guarantee you that nobody in Congress had any idea of the computer revolution that was about to visit upon sciences. So we have what I would think of as legacy legislation that's controlling now what we're doing. So Bayh-Dole, the idea was, it had two goals, and one was, let's make funding agency policy more uniform. If you are interacting with Department of Defense or you're interacting with NSF, it shouldn't be widely disparate, particularly with ownership of the output of the research. And the most important impact is Congress felt like there was an enormous amount of discovery, invention, and innovation that was remaining locked in the ivory tower. And if we could only open that up, then other people would be able to use this technology to start companies, to commercialize, to create jobs. And this is really what pushed this act through. And so that's something that, if we think of the late 70s, right, that's what they were thinking. And so now this is having deep impacts on data sharing and code sharing, because the vehicle they chose to incentivize the release of the discoveries and the inventions and the innovations that researchers were coming up with was the patent, and as we all know. So now we have these tech transfer offices, and the whole idea is facilitating the patenting of work so that it can then be licensed and commercialized. So you have an incentive to get it out there because you can get licensing fees from the work. So this now is in a head-on collision with notions of reproducibility, where we want to share code and share data, because of course software is often patentable. And this is now of deep interest to tech transfer offices. So we have a conflict, and now this is legislation that even we, like computational scientists, maybe couldn't have seen coming. But software has become enormously important in this discussion in terms of patentability and what I'd like to advocate, which is the open sharing for reproducibility purposes. Okay, so what's facing scientists? So I'm sure everybody already thought of quite a few. I did a survey a couple of years ago of the machine learning community, and I surveyed people who had registered at NIPS, the Neural Information Processing Symposium, one of the most prestigious machine learning conferences. And the survey itself could be the subject of an entire talk, but I excerpt one result here for you where I asked them, if you didn't share the code and data associated with your last paper at NIPS, why not? So I sort of loosely put these in order, but you can see how people prioritize these reasons for not sharing code and not sharing data. And the first one, probably the one that everyone thought of right away, is it's just a lot of work. It's a lot of work to clean this up, to document my data, make sure people can understand it. It's probably even more work to clean up code such that other people can use it and understand it. And I had one researcher even put a comment on that this time to document and clean up is important, much more important than any of the other factors on a log scale. It was that important. Okay, people don't want to deal with questions from users. They're worried about receiving attribution. They'd like to patent. There's other legal barriers like copyright that prevent them from sharing. They don't want to go through verification with administration, for example, if HIPAA's involved. At the NIPS conference, there's a strong medical component, so they have a lot of imaging data or patient-related data, so this would come up in that context. They're worried about future work being stolen. So this is one, but you can see that's about a third of the people are worried about loss of future publications, certainly lower than I expected in terms of not wanting to share your code and your data. So people are less worried about that. They don't want to advantage their competitors, and then they just don't know where to put the stuff like they just don't have enough space to actually share it. Another one that I certainly feel as a junior researcher, so we have a guy sitting at a desk with a senior person, and the senior person saying behind one door is tenure and behind the other one is working at McDonald's. It's just the enormous amount of pressure that young scientists can feel to conform to standards that will get them tenure. Okay, so the next topic builds on the survey. I'm going to go deeper into a couple of the issues that scientists mentioned they were having trouble with, particularly right now the legal issues, so access to scientific knowledge. Okay. So journals and journal requirements. So this is work that I'm in the middle of now, so this is very preliminary results. What I've done is looked at computational science journals by ISI field classifications, and we've come up with 170 journals, and we went and looked at what their code and data requirements were. So in the summer of 2011, there were 15% of these 170 journals had a data requirement. It may or may not have been enforced, but they had a stated requirement. And I have in these, I think I had statistics and computational biology and a couple of other related field classifications, but the biology emphasis comes in with this data sharing requirement. So this is a little high because we're in bio and genomics world. 7% required sharing code. So this I thought was fascinating. I think before I started this, I would have been surprised if one had it. But we have 7% with requirements of code sharing. And the proportion requiring supplemental materials is 9, even though, of course, many journals will host, but this is requiring. And then the proportion that are open access is about 60%. So I don't think I have the table in here, but those requiring code and requiring data, these tend to be journals that are very strong, very prestigious, have high impact factors. For example, Science requires you to relinquish code and data upon request to anything that's been published since February of this year, and they'll retract if you don't. So it's these types of journals that are in very strong positions to make such demands on their authors. Okay, but journals are subject to all sorts of problems as well as they try to move towards reproducibility. So what are the standards? If someone shares code and data, how do you actually check that that's really something that's of use to other people? What are standards for metadata, for archiving, reuse, documentation? What are the sharing platforms? Can you use any sharing platform? There's big debates about review. Is review something that happens to code and data? Should it for reusability? Or is this something like the approach science has taken, something that's done by the community post-publication? And in a sense, if you think about our legacy in experimental science, this is also what's happened in experimental science. The reproducibility happens after publication. You give them the tools for reproducibility, but you don't necessarily verify that it is reproducible. So this creates a lot of burden on authors, particularly authors that don't have strong computer science backgrounds and aren't as well versed in using the tools or how they might go about sharing the code and the data. It can also affect when you would publish. So if you have early evolving research, it's a disincentive to publish early in that cycle to share the code and the data. So you might adjust when you actually are ready to produce the work if it involves also producing the code and the data. And then, of course, like I just mentioned, all the journals want to attract the best papers, so making it more difficult to submit to the journal is something that goes against that. Okay, I wanted to throw it here also just as something to think about, how we cite code and how we cite data. There are lots of arguments and discussion about how this is one of the key missing elements, and if we had a way to give credit to people who are sharing code and sharing data, this is something that would really transform the standards of reproducibility in computational science. So there's lots of problems that other aspects of the changes in science are bringing about. Like, for example, the data deluge. How do you cite a journal that's been annotated by, say, 25,000 people? And so it's not something that's as simple as the type of citation that we've seen up until now, and there are new complications that are coming in. How do you cite the web versus published articles? And how do you do that microcitation, for example, in data sets or even in contributions to code bases? There are enormous issues around versioning and how you attach versions to published work. And of course, data sets are corrected and updated all the time. Code evolves, particularly big codes that are geared towards one project that can be a many decades long process. How do you, or whether you, acknowledge citizen contributions? As all this openness and transparency in science is coming about, citizens are becoming more engaged in making contributions to the scientific enterprise. And then, of course, the big questions. How do you develop the code? How do you review the code? What happens to it a year from now, 2 years from now? What systems does it need to run on? How open do you really have to be? How reusable does the code have to be? OK, so here are some of the legal barriers that I actually have a little bit more of a solution for. So I mentioned earlier in the talk how legislation had been passed that affects computational science. So this is one of the biggest examples of legislation that they had. Congress and the White House had a particular end in mind, but it's come to affect our work as we become more digital. So the example I'm thinking of is copyright. So copyright is something that's embedded in the Constitution. The Constitution says to promote the progress of science and the useful arts by securing for limited times to authors and inventors the exclusive right to their respective writings and discoveries. That really does sound like they're talking to computational scientists in a way. So what happens now after the law has been enacted and interpreted over many, many years? Any original expression of an idea now falls under copyright by default. So what this means is you write a paper, you have copyright on this by default. You write code, copyright falls to you, the author, by default. Data is a little more complicated. Congress has ruled, the Supreme Court has heard cases and made case law that there's no copyright inherent in raw facts. But there is copyright inherent in the original expression of these raw facts. Now, they were dealing with phone books. I don't know how to interpret that for computational science or even how we would define a raw fact, but suffice it to say there can be an element of copyright in data as well. Almost any project does some sense of original and selection and arrangement of facts that they're going to use in their research in data sets. So what copyright does is quite nefarious from a computational scientist's point of view. It gives the author exclusive rights to reproduce the work and prepare derivative works based upon the original. So now what that means is if I want to use your code in my project, I have to ask you and get your permission, and unless steps are taken otherwise. Otherwise, it's illegal. And this isn't pending. I mean, this is the way the world is right now. Same with data, because there's a possibility there could be copyright in the data. And of course, it goes for your tables and figures and your writings as well. Now, there are exceptions and limitations. For example, fair use. They won't cover scientific research as a whole, but, and I won't go into them in detail, but there are small exceptions that you can argue around copyright that don't require you to ask permission. But essentially, copyright has produced a permission-based culture for computational science. So this is not the first time that people have noticed this. Richard Stallman was, so the story goes, upset with a new printer they got at MIT where he could no longer modify the source code in the printer to say, for example, send a message if there was a paper jam or something like this. And he developed what probably many people are familiar with here, the GNU public license for software. And this has been an enormously influential license and has helped create the open source software communities that everyone, I'm sure, is familiar with here. So what the genius in his approach was, he said, I can upfront attach a legal notice to, he was talking about code, to the code that I'm sharing, saying, here are my terms of use. Instead of using the default copyright terms of use, I'm going to just give you these other terms of use. For example, you're free to use my code however you like if you just attribute me. GPL has a few more restrictions in it than that, but you could say this, and then everything I discussed about copyright and the restrictiveness of copyright would no longer apply. Copyright still underlies the licenses. It doesn't go anywhere, but what's happened is now you've turned it into a contract. And in a sense, you've given permission in advance. And of course, this is Stallman's work has proliferated. There's so many open source licenses now. This approach has taken off like wildfire. There's hundreds of them. Larry Lessig, who was a professor in the law school when I was there at Stanford, took this approach and thought, well, there's no reason to just apply it to open source software. There are other people who are subject to copyright who also want to share their works. And he was thinking specifically of artistic and creative works, for example, MP3s or film or images and putting images on the web and so on. And all of that would, of course, fall under copyright by default. Stallman's open source software licenses wouldn't apply to, say, a JPEG in the same way they would apply to some C code. So what Larry Lessig and two other people, Hal Abelson and Eric Eldred, they founded Creative Commons and did essentially the same thing as Stallman, came up with some pre-written terms of use that people could use when they wanted to set their own permissioning for artistic works that fall under copyright. So he distilled it down to 4 restrictions you could place. Use my work and give me attribution. You can use my work, but I don't want you to use it for commercial ends. Use my work, but I really don't want you to build on it and create derivative works from it. So for example, if I share an image, I don't want you including that in your collage that you're building or something like that. And then the last one, and this one does come directly from GPL, this share-alike idea. Any derivative work must carry the same license as the original, and the entire library of work will come under that same license. So what I thought in 2009 is there hasn't been a real evaluation of the licensing structure that's appropriate for computational scientists who want to share code and want to share data. So I developed the reproducible research standard, and what it does is it makes licensing recommendations that are suitable for our scientific norms. And the goal is, instead of inheriting an intellectual property structure from Congress, we can then use these to set the terms at which we permission our work to be shared much more closely to our norms. Instead of having barriers to reproducibility and sharing, we can actually open this up and permission it with attribution, typical for what we would normally do. So the idea was release your media components, like your text and your figures, and things that would naturally fall under Creative Commons with the Creative Commons attribution license. Release code components under an attribution-only license that came from open source software world. So there's a few, like modified BSD, for example, extremely lightweight licenses. All you would need to do is give attribution. Data is difficult for the reasons that I mentioned earlier. So one approach is simply to certify it as in the public domain. Or you could lean on that original selection and arrangement of the raw facts and attach attribution-only license to this. So if there's a residual copyright in the data. So the idea was to take copyright's barrier to reproducible research away. That's not the only barrier. So there are lots of other barriers, which I'm not saying they're not legitimate, but they're barriers that we would need to think about. So there's lots of privacy concerns and HIPAA regulation about sharing data. Like I mentioned before, the incentives to patent and commercialize. If you want to collaborate with industry, you're subject to a number of other agreements that you would need to think through how that impacts, or how, for example, using the reproducible research standard would impact that collaboration. There's rules at the institutional level governing what happens to data and what happens to code that you would need to work through. I mean, we all signed when we were hired by our institution. We turned over ownership of inventions to the institution. So, and this is something that's a fallout from Bayh-Dole. The thinking wasn't about reproducibility. Okay, quickly on tools and platforms. Much of the software that we use for computational science, we have inherited from people who have developed it not with science as the end in mind. So the thinking was more along the lines of, I have a problem, I have a question, and I want an answer, so I boot up the computer, enter my questions, and then I get an answer. And that's done. So what changes about that in the scientific context is the idea of sharing and collaboration. So it may be now important that I'm able to let my collaborators and co-authors know what I'm doing as I'm going through the process of working on the computer. This is generally not facilitated in most of the computational science software that we have. And then at the end, if we're sharing and we want to tell other people how we actually got to our published results, there's not a convenient mechanism for saving what we've done as we go, or being able to sort of package up dependencies and making that available. So and it stems from this idea of a dialogue with the computer as opposed to an entire workflow. Okay, and of course all these things from tools from error quantification and validation, verification, unit tests, regression tests, even when code is shared, there isn't the same standards as, say, in the open source software community for reliability and versioning and how we develop systems for opening code collaborations and also generating community building. So all of these are still open questions that we're just starting to touch on. I was involved in organizing a workshop this summer with Randy Levesque and Ian Mitchell. And what we were interested in, we called it Reproducible Research Tools and Strategies for Scientific Computing. We were interested in bringing together members of the research community who had been starting to develop these software tools. So I think maybe I can just very quickly just show you the webpage. Okay, so at the webpage, we put all the video and talks and slides online. And so we had 2 days of talks, and people, so I'll touch on this in a little more detail, but people were developing, presenting code packages that they'd developed to permit people to, say, run code on another person's machine or track the work as they went through and did their computational experiment. And so there's really now beginning to be a very active and engaged community in software development for computational science with an eye to reproducibility. One of the things that was presented is viz trails, so the idea, I think I might have a picture coming up, the idea that you can track dependencies in your functions for replication and for other people to understand your work. And there are a number of other groups, Gene Pattern, Taverna, working on this. Another thing that was presented is a system where there could be automatic repository in the cloud as you generate the figures. So if you're working in MATLAB, it would store code and data if there is any in the cloud. And then you would have a unique identifier that would allow others to go and regenerate and access that code and data. Okay, so here's just a couple of examples of work that was presented in the summer. So on the left is viz trails, and you can see they're doing brain imaging, and in the background they have how they work. There's sort of their flow chart on how they worked through their code that was doing the analysis. And you can see it in a visual way. On the right is a joint effort between Broad at MIT and Microsoft, because you can see it's in Word. So the idea is they develop these pipelines, what they call pipelines for research. And you can see that on the right, that you would be able to take this figure and open a pipeline and see how the actual figure was generated. Okay, so I did want to mention, getting to the end of my talk, that this is really not something that a few researchers have curmudgeonly started complaining about. This is something that many different fields are starting to discuss and starting to engage with and realize the seriousness of this issue. So again, it's a little bit of a blizzard of words, but there's an enormous amount of effort that's coming from applied math and coming from geosciences. You can see workshops and special sessions at conferences dedicated to these issues of computational reproducibility. Biometric Society is taking on these issues and wondering about the reliability of the results that they're publishing and how do we incorporate notions of reproducibility into our work. Even in computer science at the ACM SIGMOD conferences, one of the tracks required the results to be verified. So you would submit your code, and the results would be regenerated as part of the application process to the conference itself. So I'll leave you with a few thoughts, and there are many deep challenges, I think, to this notion of open science or reproducible research that people throw at me from time to time. And one is I've coined it the Taleb effect. So this is the author of The Black Swan, Nassim Taleb, and he talks about the danger of having very sophisticated mathematical tools being used by people who maybe don't understand the ramifications of using these tools. And this argument has been made to me as well for sharing of very sophisticated computational codes from science and also data. And if people did find it easy to access and use this, then possibly this could create dangerous results. So it's something to think about. Even if we could share code and data, so my background, I feel, in a sense, I was very lucky. We worked on short MATLAB scripts, and it was fairly easy to share our work. And this is not the case for many, many projects, especially as you scale up. So in my case, reading a MATLAB script to understand what another researcher had done was not particularly onerous. And there's certainly work that's being published from code bases, even if you wanted to read it and try and understand it, it just would take you years, and it's just not a practical endeavor. So the idea is, how do you work around what there will necessarily be opacity in software that's shared? So do we develop more sophisticated ways of testing the software to understand what it's doing and to verify it? But it won't be the case that it's some, one-pager where you get to look and see that, okay, n was 50 or something. I'm also thinking about issues where software being made readily available and not being custom built for the particular project at hand, or even the one research question at hand, might make it easier to use this software, in a sense that that's the idea behind it. So does this make it more difficult to innovate in terms of the software that's being used on computational data? So this goes back to one of my first slides where I said how intellectual contributions were now being stored in software. And of course, software is very difficult to write and create. And so if you can use something that someone else has written and that's facilitated, are you then also using that person's thinking or those people's thought in analyzing your project as opposed to coming up with new ideas? Are we discouraging independent replication? So if you can use someone else's code and data to regenerate and check their results, does that prevent people or disincentivize people from actually rewriting the code and working from the data and seeing if they can actually independently generate the results? One question that I'm familiar with is people saying, well, there isn't a scientific contribution in just being able to take code and take data that someone else has prepared and just run it and get the same results. So I think the argument is that we really need both. If we do have a system where there's independent replication of the results, people rewriting the code and regenerating the results, it's almost certain that they won't come out to match exactly the same. So open code, open data is necessary to reconcile the two different versions of the results. So in a sense, we need both replication, in the sense of being able to take code and take data and regenerate results precisely, and also we need the independent validation from an independent instantiation in software and recreation of the results. What I was hoping to motivate you earlier in the talk was the important need for engagement by scientists, and especially the computational science community, in policy discussions that are happening now in Washington, and how much of that legislation and the results will come to influence us. Okay, so I'll leave it there, and I put up a few references that are all available on my website, and the slides themselves they're also available on the website.
the OSTP, American Competes Act.
Mm-hmm.
In the text there, it said something about government data. I mean,
Yeah.
is data that the government pays for government data? I mean, you know, there's these 2 RFIs that are out there right now that we are being invited to answer. I mean, I'm just wondering if you can give us some more guidance about this whole thing.
Yeah, no, thank you for mentioning those RFIs. So what Brian means is that so about 2 years ago, about this time of year, the White House Office of Science and Technology Policy said, we want comments from the scientific community about open access. So this is a follow-on to that, and they want further comments. And they are extremely interested in this issue and could do something about it. I don't think people know the answer to data ownership. And what I believe, just from conversations, what they mean when they talk about government data is literally health and human resources data that's being generated within the agencies. And there's been even more discussion about that type of data in OSTP than about scientific data. And you may be familiar with data.gov, for example, where the government data is being shared. So I think we'd be pretty safe in making an assumption that what data.gov is referring to, the data coming out of, Department of Labor or whatever it is, the internally generated data from the government is what they mean by government data. And I wouldn't assume that even though grants are coming from the government, that it's government data. And we can trace back through ownership agreements that probably there's an argument that it is probably institutional, but it's an open question. So one of the interesting things about this work is we are interacting with more and more regulations because of our online presence than we ever had to in the past. And so that's been a theme that they may or may not apply to us, and we're certainly strange cases. And there isn't law that necessarily speaks to everything we do.
Sorry, I have a question. It seems that ironically I asked just about the same question in the last meeting we had in this room. It seems that the push to first-to-file patenting would be the nemesis of your whole proposal here, because somebody could patent your own work right out from under you.
It's an extremely good point. So one of the things that's important in patenting is that there isn't prior art in applying for the patent. The patent has to be novel. And so by putting your work out there, you create prior art and make it more difficult for others to assert a patent. But I think you're exactly right, and I think that we'll see how this plays out. And I think other researchers talk to me how their interpretation of this is that they have to rush to patent their own work just to make sure someone else doesn't patent their work. And so it's creating this incentive towards patent. And this is, I think it's just an incredibly deep issue. And it certainly wasn't thought through in the late 70s when Bayh-Dole, that's the source of all of this, was passed.
Well, doesn't first to file actually eliminate? Sorry, doesn't first to file essentially eliminate prior art as being your defense against patent infringement?
My understanding is it doesn't eliminate it. What it does is it makes it so that it's literally the person who hands in their documents applying for the patent first who gets it, whereas the previous system was you would show that you had worked on this in 2001 or something, and then you could assert patent rights, and you had a certain window to do that, and so on. So I don't think it takes away the novel aspect of it, but I mean, it remains to be seen how it impacts the scientific community. But again, so this was a law that didn't come out of consideration of impact of the scientific community. It came out of uniform standards. We were one of the only countries that doesn't follow first to file. And so there's sort of international pressure on the US to align itself with other countries, and we just have to deal with that, with the consequences.
Hi. You, at one point, were talking about some of the practices of open source software, like unit test, regression test, versioning, data provenance, and how reproducible research hasn't perhaps caught up in some of those techniques and approaches. Are there any really ripe, low-hanging fruit from open source software that reproducible research should just start doing?
The only one I can think of is, I know GitHub is very interested in scientific research, and they're very interested in facilitating the collaboration aspects of scientific research. And plus their interface, the web interface, seems to be a little easier for people who are not as familiar with version control. That's the only one I can think of that's low-hanging fruit, and I know for some researchers that's still a barrier to use. They're still not comfortable with GitHub. Maybe I should, let's see. I should go back to this website. Some of these were, I think, quite ingenious. So for example, CDE, what they do is just trace dependencies in your Linux system and then package up those dependencies so that it can be run fairly seamlessly in another Linux system. This is a fairly straightforward approach to reproducibility if you work on a Linux system where that's possible. And so I think these first approaches, they're sort of rough cuts at the low-hanging fruit here.
Much of what you talked about seems reference to the United States.
John, can you wait to get
Much of what you've talked about seems reference to the United States. If you take a global view, does that modify some of the perspectives that you would share or guidance that you would offer?
Yeah, no, it does, particularly in the legal domain. So tool use and so on, it's not so vital where you actually are. But for example, the very brief discussion I gave about copyrighting data and how that works in the US, data is copyrightable in Europe. So now many of us have European collaborators, and if there's data generation involved, the legal strictures on that data are totally different in Europe as to here. So what I've done was absolutely Eurocentric US-centric for release in the US, but you would need consideration of the different way that copyright is interpreted, for example, in Europe to release it there. Having said that, the EU seems to be moving towards open science a little faster than we are, perhaps. And I just read about an open science repository that the EU is funding in Finland. I think the idea is to house scientific data as a larger repository for all EU. And that's more progressive than what we've got here, for example. So it's, in some sense they're moving faster and there's more facilities there. In another sense there's more barriers, particularly in copyright. But it's certainly something that needs to be ironed out.
There's going to be massive output from Asia, then what?
Yeah, no, that's exactly right. Exactly right. So I think...
I asked a question and you said that's right.
So in the sense that we'll need to work out all these differences, and it is not worked out at the moment. So that's what I meant. In terms of where the data is stored and how there's access, and you don't want to access data in, say, Europe and violate copyright because you're an American and so on. And one thing that is sort of, I guess, the silver lining on something like the first-to-file requirements here is that there are efforts internationally to standardize and align IP law. And in my opinion, they don't do it in the best interest of computational scientists, but the alignment itself is helpful for sharing code and sharing data because of, international collaboration is part and parcel of everything we do.
So not to make the problem more complex, but we've been centering a lot on sort of intellectual property and getting rights to the data and programs. Increasingly in this sort of large-scale science, simply getting the computational power necessary for somebody else, even if everything else is available, we're talking about stuff that, massive data sets and massive simulation. You're talking about ClimateGate, the ability to simply get the computational environment a year later to be able to rerun this is adding to the complexity. What do you see being done there?
I think that's exactly right too. But it's adding to the complexity, and it adds to it in very interesting ways. So if you want to allow people to reproduce your results and your data is several terabytes, it isn't the case that you can just throw it out there and expect people to reproduce it. So there's another whole hosting mechanism that you need to think about. And there's lots of discussion, well, this is something that's an ideal repurposing of the cloud for this kind of thing. And some of the discussions at NSF have pointed out that we don't, as a federal funding agency, we don't have really realistic capabilities to catch up to the implementations of the commercial cloud. For example, it's just so, the scale is just so much larger. And so then it opens us, so not to make it more complex yet again, but it opens up the fact that perhaps for sharing these extremely large data sets, large simulations, you are using commercial vendors, for example, if you want to be more open about it, or sometimes even to do the work at all. And so there's very deep concerns that people have about involving a commercial community that doesn't have the same ends as scientists in the discussion. At this stage, I don't have a solution for that. For the enormous scale problems you're talking about, that may be where we end up going.
Sometimes unclear to me is once you publish your paper in many journals, it seems to me that the data, the figure, the code, the copyright belong to the publisher. So if you want to reuse that, you might need the permission from them. Is that right?
That's exactly right. So that's a sister issue that's essentially what's motivating behind the open access issue is in terms of ownership and sharing of the actual published paper itself. So I think there are envelopes that can be pushed there, and I think in many computational science communities, certainly ones that I'm familiar with, it would be absolutely standard to throw your paper out on the web at the same time as you're publishing it. We never gave it a second thought. So I think the deeper question, I think you're absolutely right from a legal standpoint, but the deeper question is, well, what's the enforcement that the journals are going to really exert over this? Traditionally, they haven't exerted a lot of enforcement. And then there's movement I'm seeing in my work on journals where it's starting to be permissible to cross-post an archive, for example, which is, in a sense, also kind of an open access approach. Another approach that I'm working on, a project that I have going on is, well, how can we give scientists the tools when they're signing the copyright agreements with the publisher to amend them in such a way that it doesn't necessarily hand over the copyright point blank to the publishers. And publishers are aware of open access issues, and there's more leverage there than we think we have for rights over our own work. So this is also an evolving issue. That's absolutely right.
Yeah. So research topics and methods, they may find their way into the undergraduate classroom. So what I'm wondering is, would you see the same tools that would help you reproduce research results also help you to confirm that a student or a group of students, they submitted their own work, say, for an assignment? And then also, do you see a role for this type of approach even in assessment? I think one of your slides you talked about sort of a dialogue between the researcher and the computer, and it seemed like that would be sort of an opportunity to assess a student's level of understanding or their thinking processes. So I'm just wondering, do you see opportunities for applications in those areas?
That's a very interesting idea, and I haven't given it enough serious thought to really make larger than sort of general comments. One of the things that's very interesting about this work, it's another byproduct of reproducibility, in sharing scientific results in a reproducible way, in an open way, it does open the use of the methods to more than people who are in a small community who happen to know each other and can maybe share codes among themselves by email. And so you end up with this situation where talented undergrads could maybe start fooling around with some signal processing results or something like this. I haven't thought about how to use that in terms of assessment. I have used GitHub in one of my classes and had assignments handed in through GitHub, and the students learned to use it pretty quickly. So, I mean, you can certainly, I think there's lots of room for creativity in the classroom.
I'm going to take the prerogative to ask the last question. Further down that slide, there's a... We have one here, too. Oh, okay. Sorry. Well, the next to last question. The executable scientific paper. Could you say just a little bit about your thinking on the relationship between the agenda you're describing and possible modifications to scholarly communication?
Yeah, that's a very important question. So this papier-mâché paper was a finalist in the Elsevier Grand Challenges about the executable paper they held last year. And I had concerns about this, and in talking to some publishers, they didn't seem necessarily aware of this issue, perhaps on purpose. But the idea that you would submit, so this is the broad idea, and it's still something that's evolving, but the idea is that when you would submit your paper to a publisher, you would submit code and data, and the package itself would then be published, and you could reproduce perhaps within the paper. You know, the dream would be something like you're reading along, and you just click on the figure, and you can regenerate it, and so on, in S-weave type way. My concern with this is the intellectual property concerns. If we're handing over our paper to the publishers, I don't know if we'd really want to hand over rights to the code and rights to the data. That seems like handing over all our scientific crown jewels to a publisher that would then, as we know from history, would keep it locked down. So that's something where I was concerned about that aspect of the executable paper. But the idea of the publishers holding this, but the idea in general that papers could be delivered in such a way that they're almost a seamless triple with the paper, the write-up, the narrative, and the code and the data is extremely attractive. And that's something that people have talked about. Robert Gentleman coined it a research compendium. And we should be talking in terms of research compendia rather than as papers. And there are tools, like I mentioned, S-weave, for example, to help facilitate that idea as well. And these are all things that are bubbling up from the community level, and use cases are around that particular developer's experience in computational science. So they may not be universal solutions, or they may be something that's extensible to different communities, but there's experimentation going on with this concept, for sure, and people are rethinking the concept.
Okay, last question, 2 very short points. One, you talked about amending the copyright contracts that we sign with the publishers. There is support on campus for this through the copyright office in the libraries. Melissa Levine is the contact. She helps amend contracts. There was one journal that I was on the editorial board for them. They switched from open to closed, refused to negotiate, refused to allow amending of the contract. I withdrew from the editorial board. The question I had was one of the ways of getting things out. I mean, I noticed you have your own domain name, but social media is used for conversation, collaboration, and getting things out. You said the slides are on the website. I'm going, why aren't they in SlideShare, where people can embed them in their blogs and continue and extend the conversation?
Yeah.
And I'm wondering, do you have a blog? Are you using social media as part of this dialogue?
So those are great points. This idea, this sort of modality is just old. I just learned it in how to communicate from my advisor in early 2000s, and it just sort of stuck around. One thing that I've been very minorly involved in an advisory role is EarthCube, and I think people maybe are familiar with EarthCube. And they did it all in Ning, right? All in social media platforms, and it's all about collaboration and community building. So I think there's definitely more that I do have a blog. It's just blog.stodden.net. I don't blog there that often, but once in a while I put something there. And then the way that I've used social media, people have people especially, I don't want to call myself old, but I certainly feel old compared to other Facebook users. But so people have reservations, for example, in Facebook using me because of privacy and so on. So, and the way that I've repurposed Facebook is simply around my work. So, so Facebook and Twitter, I try to talk about things that I think are interesting that are happening in this topic, and I don't use it so much for, I hung out with Bob last night or whatever a lot of the users do. So in that sense, but I think these tools are evolving. So, so your point about SlideShare is well taken. SlideShare has some limitations. Last time I looked, you're limited to 100 megs. So I don't know who makes slides more than 100 megs, but I have seen a couple of slide decks that are really big like that wouldn't be accommodated. And and then there's the other idea which is this tension between science and private industry. So what happens if I really just stick all my slides there and my hard disk dies and I don't have copies and SlideShare is out of business, or they decide to repurpose the material in some way that's not as open, for example. So SlideShare may be optimizing our next step right now. But I think as a community, we can catch up and sort of learn from these sharing modalities. And that was part of what we were trying to do with this conference is, well, how do we really kind of advance the tools and the infrastructure underlying sharing and underlying reproducibility?
Thank you very much.